Okay, let's move on to the next talk of this session. Alex McDonough from UC Davis will talk about fragmenting any parallelepiped into a signed tile.
All right, thank you very much. So this project actually began at a virtual conference in Israel at FIPSAC a few years ago. I gave a talk on a certain tiling that I discovered, and then Joseph Doolittle from the audience asked if maybe there was a way to generalize it, and it turns out there is. It turned out to be quite interesting, and that's what this talk's about. So thanks to the organizers for inviting me here. Also, I'm on the job market, so if anyone wants to give me a job, feel free. And let's get started. I will mention everything's going to be a bit vague because there's not too much time, but I really want to focus on examples because I think that paints a picture of what's going on. So we're going to start in the two-dimensional case. And I'm going to use this notation for the parallelepiped formed by the columns of M, where M is just any matrix, but for now we're going to choose this specific one. So in this example, this is the origin, and we can see that the first column goes like this, second column goes like this, not that far, and it all connects out, and then we get this parallelepiped or parallelogram in 2D. And if we want to find the volume or the area of this parallelepiped, the way to do it is to find the determinant of the matrix. And when doing the calculation, we will find that it is 2 plus 4, which is in fact 6. And I point this out because one question you might ask is, can we see this 2 and this 4 anywhere in this parallelogram? Is there a way to sort of divide it into some region of area 4 and region of area 2? And is there a way to generalize this idea? And this was, in different words, the question that motivated me to look at this kind of problem. I was specifically looking at a certain co-kernel, so that's why I mentioned the co-kernel down here, but if you're not interested in co-kernels, feel free to ignore that. And I wanted to figure out if there was a natural way to split this up into the pieces that make up this determinant formula. So what ends up happening, here's the parallelogram, and a fact which is always true for every parallelepiped of any dimension is we can get a tiling by just translating this parallelepiped along its facets. And this will always work. I mean, if you're invertible, you'll get a tiling of everything. If you're not invertible, things get a little degenerate, but we're just going to focus on invertible. And so from here, I'm going to do something that probably isn't going to make a whole lot of sense. I still don't fully understand why this is the way to do this, but it ends up giving some fascinating things. So we're going to introduce two new matrices. I'm going to call them S1 of M and S2 of M. And for S1, I'm going to zero out this diagonal, and I'm going to negate the second row. And then for S2, I'm going to zero out the other diagonal. And again, I'm going to negate the second row. So this is how we get these two matrices. You could do this for any 2x2 matrix. And from here, what we can do is get the fundamental parallelepiped of each of these two new matrices. So in this case, the first one, we get a rectangle. The second one, we get a square. And I have them drawn in here where that little black dot right here is the origin. And what we could do is we could draw this same shape at every one of these different points. And notice that these are the same points that we get on the left. It's just the integer translates of the parallelogram M, or the fundamental parallelepiped of M. And I'll start drawing a few on here. What you'll notice is that this actually gives you a tiling of space. So if we were to do some more of this, we'd end up with something kind of looking like this. You can tell if you squint your eyes and ignore the purple part, you can see this tiling showing up. And so this is saying that we've now found a way to get the same, based on the same translation, we get a new tiling where instead of one parallelogram, we now have two rectangles. And another way to see this that's shown on the bottom is that if we start with this shape, that actually takes up the same space as over here. We can just do some translations. And something that's easy to miss is not only are we translating these different regions, but the purple part over here is translating by 1, -2 to get over here. And the blue part is translating by 2, 2. So this is sort of showing that these are actually equivalent mod M in a certain sense. And another thing to realize is that the determinant of S1 of M is -2. The determinant of S2 of M is -4. Ignoring the negative signs, this is exactly the 2 and the 4 that we had before. So this actually succeeds at our initial goal of now we've managed to split up this parallelogram into this region of area 4 and then a region of area 2. And this can say things about the co-kernel as well. And so this is related to the original version of the tiling. And you can try this for any 2x2 matrix. And in a lot of cases, you get something very similar to this. But there's also cases where this really can't work. So in this example, the determinant is not the sum of two numbers. The determinant is the difference of two numbers. So we have the determinant of M is 5 - 2 = 3. And if we try just naively to do this exact same construction, what you end up with, I can draw a few of the things here. Well, we're going to have some overlap on this side. And then on the other one, we're going to have some spaces that don't get covered at all. So the first reaction might be that this construction just doesn't work in this case. But actually, once we complete the process, we get a picture that looks like this, where on the left we have certain parts so everything's covered at least once, and some regions are covered twice, and other parts are only covered once. Whereas on the right, we have some parts are covered once and some aren't covered at all. And what ends up being true, and you can sort of see if you compare the pictures, is that every point is going to be covered by one more translate of the first tile than translate of the second tile. And this is true for any 2x2 matrix. Sometimes you'll get more than 2 tiles covered. You might have like 4 tiles in the first one and then 3 on the second one. But if you take this signed total, you're always going to get exactly 1 everywhere, or exactly -1 everywhere. So this is sort of the main idea in the simplest 2-dimensional case. And so this is as precise as I'm going to get here. It's certainly still quite vague, but the original version of the theorem that I presented a few years ago is that if we restrict to a special class of matrices, which I can describe pretty well, but I don't think there's going to be time to really talk about it, then we get a nice periodic tiling and a partition of the co-kernel. The new idea is if we take any invertible matrix, this same construction is going to give a signed periodic tiling of Rn. So let me just give a very brief sketch of how we showed this. So what we did is, originally we were thinking maybe we could just kind of choose the points and figure out what contains them. But it turns out that we needed to focus on the facets and look at imagine a particle going through the facets and look at when it crosses each one. And then keep track of when it enters a positive tile or leaves a negative tile, and when it leaves a positive tile or enters a negative tile, and show that this value is always constant. And then once we show that the number of things contained is constant, then it just becomes sort of a volumetric proof of showing that, in fact, it's constantly equal to 1. So way too brief, but just to give a little bit of an idea of what's going on. So a few more examples. This was my favorite example for a while. So one thing I'll mention is that if you ever have a matrix of this form where you have the sort of a block matrix, we have the identity here, the negative identity here, and then some matrix here, and then its transpose over here. Then it will always form a tiling in the traditional sense. This is the first type of matrix I was looking at in the original version of the theorem. And so in this particular example, we do a similar type of construction. We leave certain top parts and then make the bottom part negative. I won't really go into the details. And we find that the determinant of M, or really the negative determinant of M, is 1 plus 4 plus 9. And we can, if we draw these three fundamental parallelepipeds, we end up with this object right here. So this is an animation I made in Blender showing how this does, in fact, tile space. And so this is just the three-dimensional version of what we were looking at before. And now I just have one last example in 4 dimensions. And now this is a case where we don't have the nice periodic tiling. In fact, we have the also nice signed tiling. So if you have a larger matrix, we can sort of cut it off anywhere we want. I'm going to do first 2 rows, last 2 rows. We get all of the 4 choose 2 ways of choosing 2 of the columns at the top and 2 of them at the bottom. Negate the part at the bottom again. I still don't quite understand why you have to do that, but you absolutely do have to do that. And you end up with these 6 tiles here. And if we take the determinant of each of these, we find that the first 5 of them are positive, but then the last one is negative. So this is the reason why the traditional tiling won't work. We need to use a signed tiling. And even though this is 4-dimensional, it actually is possible to view in 2 dimensions. You can sort of take a 2-dimensional slice, and for this example and certain other ones, any 2-dimensional slice, if you fix the last 2 coordinates, it doesn't matter which one you choose. And what you get is these 6 different tilings. So the tiling you get from each of these first 5 ones doesn't have any overlaps, but then the last one does have a little bit of overlap. But the really fascinating thing is if we take these first 5 tiles, which were all of the positive ones, and we overlap them, what we get is this tile on the left. And you'll notice that this is very similar to the negative tile that was on the right. And so if we essentially subtract this negative tile, what we get is just a covering of the plane. And this will be, again, this is originally in 4 dimensions, but it's possible to view it in 2 dimensions, and we don't end up losing any information in this case. So thank you for listening. I think that's my time.